Hello, here's another couple of waves practice questions. Right, so here we got this question is about measuring the wavelength of the yellow light from a sodium lamp. So a beam of light from a sodium lamp passes through a pair of narrow slits, S1, S2, producing a pattern on a screen. The pattern on the screen consists of regularly spaced bright and dark lines called fringes. See figure 6.2, which is on the next slide. So there's these fringes going on here. Right, state and explain the conditions necessary for the light from the two slits S1 and S2 to produce a visible pattern on the screen. Right, there's a few things that we're going to need on this, or at least a couple of things. So we need the slits to be fairly close together. So slits close together because we need the diffraction patterns to overlap. So that diffraction patterns overlap. So that's one thing. We also want them to have a similar intensity of light, because if you've got one which is really faint and one which is really strong, well, the strong one's just going to dominate. So we're going to want a similar light intensity from each slit. Similar light intensity, so no slit dominates. And then the other thing is we're going to want to have these light sources to be coherent light, because unless there's a constant phase difference in the light from each slit, then we're not going to get a stable fringe pattern. We want to have a stable interference pattern on the screen, and that means we have to have coherent light. So we need to have coherent light. And that means, so as in a constant phase difference. I'm just going to write that as constant phi. You can write it out in full yourself. So we might want to illuminate each slit from a common source, such as a single slit, from a common source, such as a single slit. So those three things will then give us a stable pattern on the screen, which is what we're after. So next bit, so using the ideas of wave superposition, explain the existence of the bright and dark fringes. In your answer, state the condition for a bright fringe to appear on the screen at P and a dark fringe to appear at P. Right, okay, so if we start with the bright fringes then, so for bright fringes, we're going to need, so bright fringes occur where we've got constructive interference. Can occur with constructive interference, at P. So that's the first thing we need. So we can say this is where we're going to get a maximum amplitude or a maximum intensity. It doesn't matter which one you actually say on either of those. So we need the light to arrive in phase from the two slits, from S1 and S2 at P. So that's what we want for those. Now we've got the opposite now for the dark fringes. So we can say for dark fringes, this is going to be for destructive interference at P, which means we're going to have a minimum amplitude and the light will be in antiphase from S1 and S2 at P. I mean, you can write about it as saying that we've got a, so say for the bright fringes, you could say the path difference is going to have to be an integer number of wavelengths. That's fine, although you are assuming that they're going to be in phase at the slits. And then if you've got an integer number of wavelengths difference in the path to P, then they'll be back in phase again. You can write it that way. I mean, I find it easier just to write, well, they were in phase if they're going to be constructively interfering, and they're going to be in antiphase if they're destructively interfering. Then you don't have to worry about whether they're in phase at S1 or S2 or not. That's neither here nor there. So, because they can be coherent and have this constant phase difference. I mean, they might be in antiphase when they're at S1 and S2, in which case you're going to want then a different description of your path difference on the way to P. Excuse me. So I think just saying the light is in phase from S1 and S2 at P, or the light is in anti-phase from S1 and S2 at P, is just a simpler way of describing it. So that's what we've got there. This is, as we know, carrying on onto the next sheet because we've got this picture of our fringes. So this shows the central part of the fringe pattern. So the screen is at 1.5 meters. The slits are 0.6 millimeters apart. Right. Calculate the fringe separation. That is the separation X between the adjacent dark lines. Right, so how many have we got here? We've got 1, 2, 3, 4, 5 gaps over 7.4 millimeters. So we're going to have 7.4 divided by 5. So that's going to be what, 1.48. You divide by 10 and then double it, millimeters. So that was fine. Right, then we need the wavelength of the light. So this is where we're using, if you want from the formula booklet, the formula that we use when we're doing the double slit experiment. So the wavelength is going to be XD over L. So that is, so X we know is 1.48. So we've got, I'm going to run out of space here, I'll put it on the next line, 1.48 times 10 to the minus 3 to get it in meters. Then we got D, which is the distance between the slits. So that was 0.6 times 10 to the minus 3 meters, and then divide by 1.5, which is the distance to the screen. So tapping that in, well, I mean, we can see it's going to be marginally less than 6 times 10 to the minus 7. So 5.9 times 10 to the minus 7 meters is giving us our wavelengths, the two significant figures. So that's good. Right, now we've got one of the two slits is covered up. Describe and explain how the pattern of light on the screen is different from that of figure 6.2. So we can say that the fringes disappear. Fringes disappear. And we'll be left with an intent. I mean, you could even draw it out. I find it easier. If you just got a single slit, then you're going to get a bell curve intensity pattern. So you could say, well, this is our intensity with distance off to the side. Well, let's call that X. They've been calling it X elsewhere, although we have to use X for separation, but it doesn't really matter. So we can now say that we're going to get a light spread out over screen, spread out in a sort of bell curve intensity distribution. So yes, fringes have gone away, and now we're just left with this general spreading out of light with a central peak in the middle. I mean, you could also say that the maximum would have dropped because we're not going to get that constant that constructive interference. So you could say that this is, lower in maximum intensity than bright fringes, but I don't think that's really necessary. But I suppose it does. It explains the, because of no constructive interference. I suppose it does describe a change, describe and explain a change. So it's quite possibly worth putting that on there. So yeah, say that the fringes disappear, the light spreads out in a bell curve, draw the bell curve, and then say that the peak is going to be lower than the intensity than the bright fringes because there's no constructive interference. So yeah, there's a lot of descriptive work in that question, a lot of it going on there. So yeah, a nice one to practice because it's the descriptive bits that tend to catch people out a little bit more. Right, I'll do one more. Name one common property of electromagnetic waves not shared by other waves. So, well, let's do oscillating electric and magnetic fields, oscillating E and B fields. I mean, I think they'll allow you other things like, things like traveling at the speed of light in a vacuum, or what else could you have? Traveling in a vacuum is another one. I mean, there's maybe slight controversy over that, because then you think, well, what about gravitational waves? I mean, they go through a vacuum and at the speed of light. So, yeah, oscillating E and B fields, where you're only getting that electromagnetic waves, that's really getting at the heart of what's electro and magnetic about them, the E and the B. So, you know, safer option maybe, but I don't think they'll quibble on a A-level mark scheme over which one of those you've gone for. Right, now we've got a block diagram of the 7 regions of the EM spectrum labelled A to G. Are we going to have to say what all these are? Oh no, we just have to say A, C and F. Right, so, well, let's put them all in anyway. We've got gamma, we've got X, we've got UV, we've got infrared, we've got microwave, we've got radio. That's what we're going here as we're going for increasing wavelength. So, yeah, pretty easy one there for some quick marks. Right, C, an aerial question. Right, we don't get many of those. It probably won't be that involved, but it's similar to polarization when they look at it normally. So an aerial mounted vertically transmits vertically polarized radio waves of frequency 10 to the 9 Hertz. Waves are detected by a receiving aerial some distance away. So initially the receiving aerial is also mounted vertically. Right. The length of the aerial is half the wavelength of the radio waves. Calculate the wavelength of the waves. Right, so the wavelength is going to be speed over frequency. So we've got 3 times 10 to the 8 divided by 10 to the 9. That gives us 0.3 meters. Calculate the length of the aerial. When I said the length of the aerial is half the wavelength. So aerial length is going to be 0.15 meters. They're not asking for a lot on that one. The receiving aerial is rotated through 180 degrees about the axis joining the centers of the 2 aerials. Yep. Describe and explain how the output signal from the receiving aerial changes with the angle of rotation. So we can say then, so emitted signal is going to be vertically polarized. Vertically polarized. So it's worth getting that in just to show that you know. Oh, actually, it says it in the question. So even if you didn't know it, it's told you it. So there you go. So we can say we're going to get a max received signal when the receiver is vertical. So at vertical receiver. So i.e. 0 degree rotation. So you could put that in 0 degrees rotation. Then we're going to get a minimum at 90 degrees rotation, as in 0. So you might even want to put 0 there for minimum. And then we're going to get a maximum again at 180 degrees rotation. So actually you might want to say reduce to a minimum at 90 degrees and then increase to maximum at 180. So then you're saying it's starting at a maximum, reducing to a minimum, increasing to a maximum again. And it's going to go in a sine wave because we're taking components. So you could even draw it out and say, well, we're going, if we had something like this, we'd be doing a cos wave. So we'd be going down to a minimum and then back up again. So you could even draw that out of having the signal versus the angle and put that in there. So it's much the same as when you're doing rotating a polarizing filter. It's the same thing. I mean, this is what's so good about aerials, is a way of then getting our polarized waves. If we're trying to get a vertically polarized radio wave, set up a polarized a vertical aerial, and that's going to pulse those things out. So so there you go, another little bit of descriptive work there. But two nice questions really, but that's all I've got in this video.